Hello, I would like to present a project that's dealing with simulation and energy retrofit in historical building. And more in detail, I would like to show to you a project that's dealing with the forecast of energy simulation in historical building. This topic is constantly, the interest in this topic is constantly increasing due to three main reasons. That is the number of buildings that is considered historical. The second one is the need to balance energy efficiency with the value of heritage in buildings. So we have to find out a sort of balance between these two topics. And finally, also due to the low knowledge and the low knowledge about the thermal behavior of historical buildings that perform very different from newer one. So in such framework, energy simulation could very helpful for designer in order to analyze some possible degradation in building, but also in order to identify some misuse or failure in the building performances. And also in order to assess multiple energy retrofit scenarios. So energy simulation could be very useful for designer, architects, engineer, in order to forecast the real energy performance of the building. But of course, energy performance has some limitation and problems. The first one is that designer very often are not able to identify the best solution among a plethora of solutions. So it's very difficult to find out the best optimal one. And the second one is that very often the simulation results are not reliable. So it's, we have to address these two points. Otherwise, the simulation is totally useless if are not reliable. Simulations are also very useful in order to provide some suggestion to designer, to architects, to policy maker too, in order to forecast the real performance of such kind of building. These tools are very useful in order also to increase the awareness between client and designer, and could be also very useful in order to plan effective maintenance in historical building. In such context, a project that is called HEART, Holistic Energy and Architectural Retrofit Toolkit, was born. Such project was founded in the framework of Horizon 2020 program, and it received almost 5 million euros of funding. And the goal of this project is exactly to develop a toolkit for the energy retrofit of residential building in combination with a decision support system, DSS, and building an energy management system able to provide a reliable forecast of the energy performance of buildings. So in HEART, the goal is, of course, to reduce the energy consumption with two main sub-tools. The first one is the decision support system that should be applied in the preliminary design of the retrofit of the building, and also it is also useful during the operation of the building. We have two main objectives that we have to achieve in the project. That is to support and improve the decision-making process. So it's a sort of advice for architect and designer. Such objective have the goal also to speed up the process of design, of course, and at the same time, with the reliable energy performance, we should be able to promote energy efficient financing. So we have these two goals in heart. The number of partners that are involved in the project are 16. There are some university and some companies that will build or built and is building the components. These tools is designed in order to be applicable to the central part of Europe that is generally characterized by both heating and cooling needs. And it is designed in order to retrofit building of almost 4 or 5 floors. This is why, because the solar potential of this building is enough in order to reduce, in order to cover the energy needs of the building. More in detail, HART consists in some subcomponent that is retrofit components for both opaque and glazed envelope, some universal tiles that very easily adapted and integrated in existing roof generally characterized by tiles. A cloud-based platform that is the main core of this system, because it's a sort of acquisition system that gets the information from each subcomponent and set properly the set point of each subcomponent in order to guarantee the proper operation of the building. Then the smart fan coil that should be replaced, the radiator system. This is supplied by that direct current, and such subcomponents are able to provide both heating and cooling. Then thermal storage, an advanced one that is filled with PCM material, so it's allowed to decrease the volume of such component that those could be stored also in very small technical room. In the project, also battery pack is integrated, but the main important component are the heat pump that is supplied also in that direct current. Of course, all these subcomponents are linked together with a multi-input, multi-output converter that allows to exchange information and energy among different subcomponents. This is a view of the smart fan coil that should be installed rather than radiators. The important thing is that is not that the smart fan coil use the same pipe line. So it's very easy to install in historical building because we have just to remove the existing radiators and we have to link the new smart fan coil with existing hydronic pipes. While about the PV tiles, we developed this component that is a sort of strips that fit very well in dimension with the existing tile. So the width is almost the same of common tiles in the Europe. But let's see the decision-making phase, because in the project we develop a decision-making tool that allows to architect to define the proper energy retrofit. In HART, we develop a tool able to run several simulations, most than 500, and according to the result that we obtained, the software, the tool, is able to identify the most optimal solution that is not the solution with the lower energy consumption, but is the solution that balance the energy consumption with the cost of intervention. The decision-making tools, of course, also size properly the subcomponent that I shown before. During the operation phase, the cloud-based platform acquires the information from the user, from the grid, from the weather, and set properly the operation of each subcomponent. In this way, we are able to guarantee and to reduce the uncertainty in energy performance, because also the operation of the HVAC system, of the technical system, change according to the boundary condition. So in this way, we are able to maintain low energy consumption. Also, during the operation phase, the cloud-based platform allows to know if some misuse is in the building, because we have a sort of baseline that is the results of the simulation, and then we are able to compare this result with the current operation of the building. In such way, we are able to identify if, for example, some user is opening the windows while the HVAC is ongoing. So this is very useful, and the system, the tool is able to send also to the user by a mobile app some alert. For example, remember that the HVAC is switched on, but you opened the windows, so something like that. In conclusion, such kind of tool is able to guarantee a high level of performance in building, but and also it's very useful, I think, for in order to increase the investment, because investors are aware on the real energy consumption of the building. We are able to guarantee a mismatch between the simulated and the real operation lower than 5% in this way. So I would like to push to use HART in futures. The project we will finish in 2021. You can find out the link in order to download all the deliverable and more information about the project from this website. Of course, part of the analysis of the project that I shown was developed in collaboration with Task 59, because I'm linking the part related to energy simulation of historical building, and part of this research, of course, is used in order to set up the energy simulation of HART. That's all.